couple demonstrations that involve basically electric field demonstrations. We're going to use the Graaff generator to generate some fairly high static potential charges. Graaff generator is a pretty simple device. It's kind of clever though. Basically the top is hollow. There's a rubber belt that's going to spin. There's a metal cylinder up there and a plastic cylinder down there. That determines the polarity of the charge that gets attached to the belt. There's a wire brush comb that does not contact the belt down at the bottom. There's another one up at top, right here, that you can't really see. It points at the belt but does not contact the belt. Okay? So these two dissimilar metals have the effect of dumping charge on the belt. And when that charge passes by that comb, it leaps off the belt, if you will, onto that comb, and that metal strip contacts the inside of the top cone. Okay? So what happens when you dump a charge on the inside of a surface that looks like this? Any guess? Just stay there. Goes inside, outside. That's where it headed. Right. On a closed metal surface, the charges reside on the outside of the surface, right? There's no charges on the inside. Okay. So as we dump more charges on the inside, they automatically redistribute to the outside. Okay. So the limitation on how much potential or charges you can dump on the top of this dome is, one, the radius of curvature, because when you have a sharp point, charges tend to congregate there. The field is higher, and if you have a high field, it eventually will break down the air and you get a little discharge, right? So if you make it not very pointy, that means you can dump more charge on there. But that means you have to be able to carry more charge on the belt, which means you have to have the horsepower of the motor to actually keep pushing charges up on this dome that already has a bunch of like charges on it. Okay? So that's a quick explanation of how that works. I'm going to turn it on and see what we can do here. It's a pretty good day in here. So you notice as I get closer, the discharge rate increases. It's not surprising. It takes a lower potential to jump that smaller gap, so it happens more quickly. So I move it out. There's more time between discharges as the voltage goes up.
So air is normally an insulator, and the electric field gets too high, then it starts acting like a conductor and charges can jump.
For that discharge to take place, the air has to be ionized. Okay, so there's this little conducting path that's formed. Much the same thing happens with a lightning bolt. Okay. All right. So another fun thing we can do is set a pile of pie plates up on the top, and more humorous than I thought it was. That's okay. And so when I turn it on, obviously the pie plates are going to become charged just as the dome is, except the pie plates, of course, are stacked, and so they're free to move. So as the pie plate beneath the top one accumulates or acquires the same charge, of course they're going to repel each other, right? So you can probably predict what's going to happen. We get a controlled removal of pie plates. All right. So I'm going to take the Graaff and I'm going to connect. Whoops, I have this backwards. Hold on. I had it all set up before, and then made me put it on the floor. Okay. So I'm going to hook one plate to the dome, and we're going to, just for the sake of argument, say that's the negative side. There's a lot of electrons in there. And then I'm going to hook the other side to ground, or the low side. So these two plates are going to be oppositely charged. And in the middle, I have a ping pong ball hanging by a string, only this is a special ping pong ball. It's covered with graphite. Graphite is a conductor. So the charges on the ball are now free to move around, which means that if this plate is negative, that means that this side of the ball is going to become negative and this side is going to become positive, and there's going to be an attraction to the plates. Yeah, we'll turn that on and see what we get. There we go. I will pivot this because I know not everybody can see it. Okay, this is what I call an electron conveyor belt. The bolt discharges on one side, is neutral, and then is attracted to the other side. Let's shut that off. There's still charge stored on the plates, so it still goes until it leaks off. Okay? Any questions on that? Okay, we have one last thing that we're going to do, and we're going to need to move some equipment around, but we're going to require a volunteer.
I'll do it.
Typically,
Wait, do you actually need a volunteer? I'll do it.
let me, you may qualify. Typically, this volunteer needs to be female.
Got that.
And you have to have straight hair, not too curly. And I can't see your hair. You got to pull back.
Try to put some in a ponytail.
It doesn't look promising. Yeah. Well, tell you what, if we have time, we'll try two. Why don't you put on? Okay. Yeah, let's just come right down here. So, what I'm going to do let's stand there. Yeah, stand right on. And I'm going to see. Yeah.
Should I see it in better?
You should be okay. Well, we're going to stop at the bracelet.
Okay.
We don't have so much time to remove metal. So as long as you do what I tell you, you should be fine. Okay, so I just want you to put your hand on there and don't take it off unless I tell you to. Okay? If you do, it's not going to be a big deal. But, actually, you can take it off. I'm ahead of myself. So we got to do a little bit of prep here. Take your head and do this. Just kind of wag your head around. Okay, now stand back up. Very good. Okay. Now you can put your hand back on the device. I'm going to turn it on. And I hope you don't mind being on YouTube too. We tend to post it. Is that okay?
That's fine.
All right. Okay. It's if you don't want it, that's fine. So take your other hand and just do this if you can without. There you go. Just kind of you fluff your hair out. That's this. Okay. That's good. All right. Very good, huh?
Is it working?
Yeah. Okay, I'm going to turn this off. Again. Okay, you can lift your hand off. Now grab the end of this one. Uh-oh, my stick dried out. Okay, that's good.
Am I okay?
Yeah, you're okay. Get your, you want a shot?
Nah.
Thank you.
I put water on the meter stick before class, And usually when you do that, you see her hair gently go down because, you know, the meter stick conducts because it's moist, but it dried out. So you got a little bit of a shot.
Early, so see you on Monday. Look out for the